Good afternoon, everyone. Thank you for joining us, and welcome to the Emeritus Professorial Lecture Series, relatively new to the Whiting School, but this series honors our distinguished emeritus professors as they transition to a new phase of their careers. And it is truly my pleasure to be here with you today to honor James Phil, an emeritus professor of applied mathematics and statistics. Jim's research has focused on probability and stochastic processes, with work lying at the interface of theoretical computer science. Specifically, he's done extensive research on Markov chains and has co-authored work introducing and developing strong stationary duality, or SSD. Here, this is one piece of information that is really outstanding, and that is that not everyone can say they have something named after them, or such as an algorithm. But Jim created what I am told is called Phil's algorithm, and also the randomness recycler. To modify existing Markov chains, Markov chain Monte Carlo algorithms to produce samples that produce samples perfectly from a desired stationary distribution. But the point is that really, for an academic to be associated with a singular piece of work that actually bears your name is in some sense the highest honor one can achieve, and the highest accomplishment. But more than that, Jim has had a very impressive career. He's fellow of several prestigious societies, has authored many papers, particularly on the analysis of algorithms. He has either served or serves as editor for journals known throughout the mathematical community, including the Journal of Theoretical Probability. He's received several teaching awards. He's made a variety of research contributions, is a respected educator and colleague, and I've seen his CV and I've read through it. And as impressive as it is, it actually does not capture the breadth and depth of his contributions to the Department of Applied Mathematics and Statistics and to the Whiting School and to Johns Hopkins. We have truly benefited from his achievement, his partnerships, his leadership, and his contributions. And we wish him well on this next phase of his career. And I think you can give him a round of applause. And now I'm happy to introduce friend and colleague, head of the Department of Applied Mathematics and Statistics, Fadil Sentosa, who is the Yu Wu and Chao Mei Chen department head and professor of Applied Mathematics and Statistics. Fadil.
So it's a pleasure for me to introduce Vince Lisinski, one of our own. Many of us many of you know more about him than I do. I know that he did his undergraduate in Notre Dame and got his degree in 2007, got his PhD under the supervision of James Phil in 2013. He was at Hopkins for a while and was a senior research scientist at the Human Language Technology Center of Excellence. And then he went to UMass Amherst for his tenure track job, and then he joined the Department of Mathematics at the University of Maryland in 2019. And most recently, in 2021, he got promoted to associate professor. He's author of 40 plus publications and works on probability and statistics of graphs. So based on what I gleaned here, I asked ChatGPT to write a limerick about him. And so here it goes. There once was a man named Vince Lisinski who studied math at Notre Dame and JHU. He became a professor at UMD and worked on graphs and probability. He also liked to solve problems with his crew. Without much further ado, Vince, the podium is yours.
So thank you for that poetic introduction. It's my great pleasure today to introduce Jim Phil. I was fortunate to have studied under Jim when I was a PhD student in the AMS department, class of 13. Jim is a towering intellect. His contributions across Markov chain analysis, analysis of algorithms, and analysis of discrete structured data are remarkable not only for their depth and breadth, but for the cleverness of the ideas and proofs contained therein. When working with Jim, I was constantly awed by his ability to extrapolate deep insights from working out seemingly simple examples, and the joyful doggedness with which he pursued his research problems. Don't even get me started on the mathematical and grammatical precision of his writing. He's the only person I know to submit a paper for first review at a journal and be returned the galley proofs, with no revision needed. Beyond his considerable intellectual acumen, Jim is also a fantastic teacher and mentor. His course was the first I took when I started in the AMS department back in 2007, and remains a favorite of mine to this day. The way he wove probability into a coherent story sprinkled with insightful quips and humor was masterful. It's no wonder he's won so many teaching awards. He possesses a master's intuition of probability and discrete structures, and with these presents complex ideas in a wonderfully easy to comprehend way. As you'll see coming up, his research talks are really a masterclass. His mentoring of myself and his many other PhD students revealed a forbearance and generosity that I strive to match in my own career. I remember a specific instance where I think it was for my initial GBO. I had made the cardinal sin of studying an ill-defined, perhaps undefinable random sequence. I distinctly remember Jim handing me the prospectus back with a good-natured joke to break the tension, and yes, it was entirely covered in red marks, and working with me to sort out my garbled thoughts. The only time I ever saw him get even mildly upset was when I accidentally revealed the score of a semi-important White Sox game to him in semi-real time, breaking the cardinal rule of the 24-hour local blackout for sporting events with Jim. Thank you, Jim, on behalf of myself and the many others whose lives you have touched, for the brilliance and joy in which you have taught and mentored us throughout the years.
Wow. Thanks, Ed. Thanks, Fadil. Thanks, Vince, for the really, really nice words. I appreciate it greatly. But you were wrong about one thing. My greatest accomplishment in my entire academic career is, as you can see here, out Shinermanning Ed Shinerman in number of puns in a title of a talk. I realized that the bow might break under the weight of all these tree puns, but I figured some poor sap would enjoy it. There's a note of bittersweetness to this occasion, because my wife and I are, Anita and I are both deeply saddened that she's not able to attend today. She's suffering from a mild illness. We expect full recovery soon, but she's watching live stream. So hello, Anita. She's having a sort of remote watch party with my sister and maybe a couple of her sisters. So hello to Anita. Sorry you couldn't participate. That young guy on the left is me, 27 years ago at my inaugural professorial lecture. And here we are just a couple weeks ago. It's the same, you can't see, but it's the same dictionary stand that was a gift in the background there, right? So I hope she gets better very, very soon. One more word about the connection between IPL and EPL. I have all my email going back to something like 1995, okay? And in particular, here was the actual announcement from the engineering school of my inaugural professorial lecture. You'll notice three things. One, it was held in Ariano Theater, which is downstairs from here in Levering. Second thing is the green arrow points out that I talked about trees then, like I'm going to today. Third thing is that reception was held in the glass pavilion, where it'll be today. And the fourth thing, I'm more famous in the department as a proofreader than I am as a mathematician. I couldn't find any email that I sent in reply to this saying, how dare you misspell Markov? I'm just hoping that what I did was got on the phone and spoke to the person and said, please change that. Anyway, so here we go. All right, so the broad focus of this presentation is the unification of many, but not all, interesting models for random trees. And I'm hoping to paint a colorful portrait of the usefulness of probability, complex variables, and real analysis in studying random trees. This talk I watched the three, I either attended or watched on archive the three, oh, I forgot to, I was going to take off my mask. The three previous EPLs, and this will be by far the most technical of them. I hope not to scare those of you who aren't mathematicians, and I'll try to be as friendly as I can. So this talk is about mathematical trees. The study of math trees goes back at least as far as Arthur Cayley in the mid-1850s. Oops, yeah, okay. Specifically, I'll be talking about Galton-Watson trees. Many of you know about the pioneering work of Watson and Galton, but I'm reminded of Steve Stigler's law of eponymy, which is that no accomplishment is ever named after the person who deserves the notice, including Stigler's law of eponymy. Okay. So Bien-Aimé, French statistician, had talked about what are now known as Galton-Watson trees before Galton and Watson. My own interest in trees started with Bob Dobro. There's a relatively recent picture of him. He was a PhD advisee of mine, had a very successful career at Carleton College in Minnesota. He retired a few years before I did, so I managed to outlast Bob in that sense. The origin of my work on conditioned critical Galton-Watson trees that I'll talk about later on in the talk is joint work with another former PhD student, Navin Kapoor. I should mention, oh, so there's Navin on the left, the late great mathematician Philippe Flageolet, who you'll hear more about later, in the center, and myself on the right. This is the only photo with colleagues where I know the exact date. Navin still had the original digital photo from June 27th, 2002. So we know when that was taken. I'm going to try to condense, and I'm not making this up, 270 pages of papers, 3 papers spanning 270 pages into this talk. If you want to learn about the material of this talk in a more leisurely fashion, I very highly recommend the paper listed first here by my friend and colleague Svante Jansson. And at the end of the talk, I'll get to current work with Svante and another co-author named Stefan Wagner. As I mentioned at the bottom of the page, the 3-person paper is my first jointly authored with Stefan. It's my 10th with Svante, who's absolutely a gem of a person in all regards. Anita and I have names for some photos, from some iconic photos in our collection. She named this one, The Two Guys. That's Svante on the left and myself on the right. I don't know the date, but sometime in the 1990s. There's Stefan Wagner, our important third guy. I won't be discussing any applications of Galton-Watson trees outside mathematics, but I'll leave this up for a few seconds at least for you to see what applications there are. And I also will be limiting my attention to Galton-Watson trees. There are other random rooted tree models, and those have applications both within mathematics and within computer science, and also outside of mathematics, as listed here. Okay, so I've completed outline step 0 of my talk, the prologue. Next, you're going to learn some background about ordered rooted trees. I decided it's too much to say each time, so I've invented the acronym ORTS. That's not standard, but I hope you'll remember that means ordered rooted trees. Then I'll tell you about simply generated random trees, Galton-Watson trees, conditioned Galton-Watson trees, critical conditioned Galton-Watson trees, and about additive functionals. That'll set up for some actual results. Okay, so ORTS are perhaps most easily understood as a certain kind of subtree of the Ulam-Harris tree. I almost titled this slide, the tree of all trees. It's a big, big tree, an infinite tree. It consists of, it's a labeled tree. It has the root, which I've labeled O here, right? It has an infinite number of children, and the order matters. Children 1, 2, 3, and so on. Child 1 has an infinite number of children, grandchildren of the root, 1, 1, 1, 2, and so on, and similarly for child 2, and so on. Okay, that's the Ulam-Harris tree U sub infinity. Orts are ordered rooted trees are, as said, ordered and rooted. For one thing, they're trees. For another thing, they're directed trees. So all of the edges are directed away from the root. In order for a subtree of the Ulam-Harris tree to be an ort, it has to have, first of all, it has to be non-empty. So, and as we'll see, it has to contain the root as an element. Secondly, it has to be closed under moving up in the tree, right? So if I include one 1 in the tree, then I have to include 1. And it also has to be closed under taking older siblings. So I'll regard 1, 1 as the oldest child of 1, 1, 2 is the second oldest child, and so on, right? So if an ort includes the vertex 1, 2, it has to include the older sibling 1, 1, okay? So I have on the next few pages, oh, and by the way, thank you very much to Ao Soon, my current PhD student, for providing these graphics. I tell Ao, without any exaggeration, that if I were to draw these, it would take me the rest of my life per graphic. Okay, so here are examples of orts. You can think of them as induced subtrees, right? Where here the vertex set inducing the tree that's marked with the dotted lines has 4 vertices, the root 1, 1, 1, and 1, 2. Okay, there's another ort with just 3 vertices. Order matters in what I'm going to say. So even though the tree on the left and the tree on the right are both orts, they're not the same ort, okay, because the order of the children matters. Okay, and let's look at some extreme examples of orts. The Ulam-Harris tree is itself an infinite ort. It meets all the requirements for an ort, right? And the tree consisting of just the root is a very finite ort, right? Here are some other examples and non-examples of orts. The 2 trees on the left, you can easily check, are orts. The 3 trees on the right are not orts. Empty tree doesn't satisfy the requirement of being non-empty. Singleton 1, 0 is not, the root is not included. I'm moving up, so that's not an ort. And here the older sibling 1 of 2 is not included, so that's not an ort. Okay. So now a little bit of notation. A few definitions. I'm going to use notation that I borrowed from Svante's survey paper. If you're wondering what the heck character is this right here, that's Fraktur font T. I'm going to just call it curly T and maybe just T if I don't need to distinguish from other versions of T, but curly T is going to be the set of all orts. Curly T sub F is going to denote the set of all finite orts. That is, unlike, for example, the Ulam-Harris tree, where the ancestry line of the tree eventually becomes extinct. And curly T sub N is going to be the set of all orts with N vertices. Here's an easy but important fact for what I'm going to say. For any ort in T sub N, the sum of out degrees, the sum of degrees of edges moving downward from the vertex equals N minus 1. Let me maybe back up one slide to show you what I mean. So for example, here is a tree with 7 vertices, right? And the sum of the out degrees is 2 plus 4 more 6, right? And that's true for any tree, that the sum of the out degrees is 1 less than the number of vertices. Am I going the right direction? No, I'm going the wrong direction. Okay, so now I've told you about orts. Next up, simply generated trees, then critical condition Galton-Watson trees, then additive functionals, and then I move on after that. So what are simply generated trees? Well, simply generated trees were introduced by Meyer and Moon in 1978. They give a way to define a unique probability distribution on curly T sub N simultaneously for various values of N. And this is done in terms of a weight sequence. So suppose we're given a fixed weight sequence of non-negative real numbers. We then define the weight of a finite tree to be the product of the weights corresponding to out degrees for the vertices. Okay, so D plus of V represents the out degree of vertex V. So W is the corresponding weight, and we take the product over all the vertices in the tree. Okay, to avoid trivialities, I'm going to assume that W sub 0 is strictly positive, and that there exists some K greater than or equal to 2 with WK strictly positive. Okay, so how do the weights give rise to a probability distribution? It's simple. This is why they're called simply generated trees, right? We're going to let capital script T sub n be the random tree obtained by picking an element of curly T sub n at random with probability proportional to its weight. So the probability of selecting a particular tree Roman T is going to be the weight W of T divided by the sum of all such weights. This normalizing factor Zn, depending on the weights, of course, is known in language from statistical physics as the partition function. So if you're saying, oh, there's a lot of math, I need some examples, they're coming in not too many slides from now, but I have some more to tell you about. So when Trevor Noah hosted the Daily Show on Comedy Central, he had a regular segment called Ain't Nobody Got Time for That, which he would start telling news stories and then have to say, but we have no time for that, let's move on to the next. So here's a very elementary but very interesting story, and I ain't got time for it, which is that given a simply generated tree weight sequence, boldface W, there's often, but not always, an equivalent probability weight sequence, let's call it P, with unit expectation. So what I mean is a weight sequence of, so it's a collection of non-negative numbers that satisfy, here's the probability condition, they should, I have to remember what does what, yeah, here we go, that they should add up to 1 and have unit expectation, okay? To get the last part, the unit expectation, the story involves something called conjugation or exponential tilting, familiar to those of you who have some experience with large deviation theory. And the idea is the same here. We're trying to take what would be an unlikely event and make it a likely event, right? That's the purpose of exponential tilting. Okay, so there's a lot written here, but bear with me. Galton-Watson trees are defined as the family trees of Galton-Watson processes. Given an offspring random variable Xi with probability mass function P, we build the tree T recursively, starting with the root and giving each node a number of children that is an independent copy of Xi. In other words, the out degrees are IID with distribution P. So this is something that you learn in a first course on stochastic processes like our 553.426. Recall, or if you're not a probabilist, enjoy the fact that the Galton-Watson process is called subcritical, critical, or supercritical as the expected number of children is of a given particle is less than 1, equal to 1, or greater than 1. Why are these terms used? Because it's a standard fact of branching process theory that the random tree you get this way will have a finite number of nodes almost surely, if and only if Xi, the expected value of Xi is less than or equal to 1. That is only in the subcritical and critical tree cases, but it's infinite with positive probability in the supercritical case. Okay, so the Galton-Watson trees have random sizes. We're mainly interested in random trees with a deterministic size, right? And so what I mean by conditioned Galton-Watson trees are Galton-Watson trees conditioned to have a specified size, which I'll typically denote by N here. And here's something to note between the, to bridge the gap between the last two parts of the talk so far, which is that conditioned Galton-Watson trees are simply generated trees, right? And the normalizing constant in this case is just the probability that the Galton-Watson tree has size N. Forget again now, okay, this way. So we can generate Galton-Watson trees to sample from conditioned Galton-Watson trees by conditioning on size. Why do I want to home in on critical Galton-Watson trees? The answer is you can show that for subcritical and supercritical Galton-Watson trees, the probability of getting any specific size is exponentially small in that size. So that's not very good for example, for doing simulations to get a particular size, right? On the other hand, for critical Galton-Watson trees, as I'll review on the next page, the tails of the distribution of the size of the tree decay like n to the minus, the probability mass function decays like n to the minus 3 halves under the simple additional condition that the offspring distribution has finite variance. So that's a nice fat tail. You can, the expected size of the tree is infinite, even though the size of the tree is finite with probability 1. That means you can get big trees with reasonable probability, right? Okay, now for Galton-Watson trees, I'm usually going to write Qn for the probability that the size of the tree is n rather than Zn. And then you would think the corresponding probability generating function ought to be called then capital Q or something, right? Sorry, I didn't make this notation standard, but it is standard. The corresponding probability generating function is usually called little y. Why? I don't know. Okay, so why tilt to critical Galton-Watson trees? I've already mentioned. If you consider a critical Galton-Watson tree with offspring random variable xi having probability generating function capital phi, and we assume finite variance, then a key equation that will only appear, I think, once in this talk, but is super important in the analysis of Galton-Watson trees, is the one that I have highlighted here in the first display. Y of z is z times capital phi of y of z. The mathematicians in the audience will have no trouble seeing that that is obvious reflection of the recursive construction of the Galton-Watson tree. But that has some interesting consequences. So it says that the function y is the inverse of the function taking t to t over phi of t. So now you can use Lagrange inversion, and I didn't know this, by the way, the footnote, I didn't know he was also known as Giuseppe Lagrangia until I looked that up on Wikipedia. But by Lagrange inversion, you can get that that the probability that the tree is of size n is 1 over n times the probability that Sn equals n minus 1, where Sn is the sum of n IID copies of the offspring random variable xi. We know a lot about sums of IID random variables. In particular, we know the local central limit theorem, right? And that's where the n to the minus 3 halves is coming from. Okay, another reason for standardizing to critical Galton-Watson trees is that it allows fair comparisons across offspring distributions, which will be the last technical part of my talk, coming up later. Okay, so now you're way overdue for some examples of critical Galton-Watson trees. The punchline is what's in green and bold at the top of this page. Many important examples of uniform distributions over various classes of trees can be formulated as critical Galton-Watson trees. The simplest choice is just take all the weights to be 1, right? Then we're just sampling orts uniformly, orts of a fixed size, of a given size, uniformly at random. The number of orts is C sub n minus 1, where Cn is the so-called nth Catalan number, and for that reason, what I'm calling orts, you might sometimes see called Catalan trees. They go by a variety of other names as well. So in this case, Tn is uniformly distributed on curly Tn, and the equivalent critical Galton-Watson tree, I don't have time to show you why this is true, but trust me, it has geometric 1/2 offspring distribution. So half probability of having size, hold on. Probably 1/2 of no children, probability 1/4 of 1 child, probably 1/8 of 2 children, and so on. Okay, there's an example of a uniformly random ort of size 1,000. Some people draw trees with the root at the top, as I did earlier. Some draw them with the root at the bottom. This one has the root at the bottom. And you'll see that there are lots of small trees, lots of small fringe trees, right? Lots of small fringe subtrees. You would also find that the height of this tree is much larger than in some other famous models of random trees. Here's a second example. The uniform distribution on labeled, unordered rooted trees. So what I mean is, consider all orts of size n, but now ignore the ordering, right? Take the 2 trees that I had in the picture before saying they're not the same tree, regard them as the same, because you can change the orders of children and get the same tree. But now do one more thing after you've gotten to unordered rooted trees. Label the vertices uniformly at random, if it has n vertices, with the numbers 1 through n. That's what I mean by getting a uniform, labeled, unordered rooted tree. So I'm going to call that alert. Don't worry, you're not going to have to remember a bunch of these acronyms. I'm mostly going to be talking about orts, but I'll call that alert, right? What's not immediately clear, but you can check, is that can be achieved by sampling orts from curly Tn using the weight sequence Wk taken to be 1 over k factorial, then randomly labeling, and then ignoring the birth order in each generation, okay? So you can get, the moral is, you can get lerts from orts, okay? And the number of lerts of size n can be shown to be n to the n minus 1, and that means that the number of labeled, unordered, unrooted trees, or loots, is n to the n minus 2. That's a famous formula that's usually attributed to Arthur Cayley, whose name came up early in the talk, but was actually found by the first professor of mathematics at the Johns Hopkins University, J.J. Sylvester, in 1857. Ed will know, was he already a member of the faculty by then? I don't know. Okay, the equivalent critical Galton-Watson tree has Poisson 1 offspring distribution, and the distribution of tree size is something called the Borel distribution. Just as an indication of you can't get all uniform distributions, interesting uniform distributions on classes of trees by means of critical Galton-Watson trees, the uniform distribution on unlabeled, unordered rooted trees, or orts, it can't be formulated in terms of simply generated trees. Okay, another famous example, of course, is binary trees, and I'll have a couple flavors of these. The first one I'm calling full binary trees, where every node either has no children or has the full complement of 2 children, right? In this case, the equivalent critical Galton-Watson tree has offspring distribution 2 times a Bernoulli random variable with success probability 1/2. And of course, this example can be generalized to full Emery trees with equivalent critical Galton-Watson tree offspring distribution m times Bernoulli with success probability 1/m. Okay, here's the other flavor of binary trees, where a node can have 0 or 1 or 2 children, but I'm going to distinguish left children from right children. Then you can check that that's the same thing as sampling orts, or sampling, let's say, simply generated trees, with the weight sequence being the weights are 1 for the values 0 and 2, and 2 for the value k equals 1. All right. So the number of binary trees of size n is also the nth Catalan number, and that's what Navin Kapoor and I meant in a paper whose reference I flashed earlier from 2004. We called those Catalan trees, and now you see it's confusing to keep track of the different kinds of trees, especially since they often go by conflicting names, right? But I hope you won't be confused here. Now the equivalent critical Galton-Watson tree has binomial 2 1/2 offspring distribution, and again, that can be generalized to Emery trees. Okay, last background thing I have to tell you about is additive functionals. So additive functionals are important to study for random trees. These are functionals that are additive. So what I mean by that is this. Let's let for a given vertex V in a tree, capital T, let's call T sub V the fringe subtree. That's the tree consisting of V and all its descendants, okay? F is a functional on trees, little f. It's often called the toll function for reasons I'll explain in a second. And then you get the additive functional, I'm gonna say deny, yes. Okay, right, so this is called the toll function, and then you get the functional on the tree by adding up these toll values, right? And equivalently, additive functionals can be defined by this recursion, and now you see maybe why this function little f is called the toll function, is because you pay a certain toll at the origin, and then you continue down to the various subtrees. And the recent work that I want to get to is asymptotics for the distribution of the an additive functional, capital F, evaluated at a random tree, capital T sub n. And I want to do not just asymptotes for things like mean and variance, but for the entire distribution. Okay, so the talk is about critical Galton-Watson trees with finite variance, sometimes without making any fuss about it. I'll assume a little more than that. And mainly I'll be discussing sums of functionals capital F that are sums of powers of subtree sizes. So the total functional little f sub, and I'll call it little f sub alpha, is at the size of t raised to the alphth power. Okay, so what are some important special cases? Well, here's a not important special case. If alpha equals 0, then you're just summing up 1 for every vertex in the tree. That means you just get n, right? Not very interesting from a probabilistic point of view. The case alpha equals 1 yields something called total path length, sum of all the lengths of paths from the root to nodes. That's important in computer science. And from considering alpha equals 1 and alpha equals 2 jointly, you can relate results to the so-called, and now I don't know how to pronounce this, Wiener or Wiener index. I do know that our Wiener, Norbert Wiener, was an American mathematician, the inventor, the studier, one of the first people to study Brownian motion. This is a different Wiener, an Austrian-American chemist. Okay, so why did Svante and Stefan and I study these particular additive functionals? Well, they're sort of interesting in their own right because of, for example, these applications here, but they're also, they serve as prototypes for functionals that are built up in large part out of small subtrees. That's by taking alpha less than 0, and large subtrees. That's by taking alpha bigger than 0. Now you might be startled by something that you see here, which is, I said up here, alpha is a complex number. And here I'm talking about the real part of alpha. And you think like, oh, this is typical mathematical generalization. The guy isn't happy to study real powers, has to go to complex powers as some sort of rote generalization. But there's a real reason to study even if you're only interested in real powers, to study complex powers, and I'll get to that in a minute. So I've already mentioned the case alpha equals 0 is trivial, but there is sort of an alpha equals 0 version that's interesting, which is instead of taking little f sub 0 and capital F sub 0, take the derivative of little f alpha and capital F alpha as alpha tends to 0. And then you get the functionals that I've listed here in the second bullet. These are called the shape functional for reasons I ain't got time to tell you about today. But this shouldn't really be called the shape functional in the Galton-Watson context. It really did deserve to be called shape functional in another context, and that I introduced the term shape functional. Anyway, I don't have time to tell you about that story. Okay, now I just have a few minutes to tell you the rest of the story. So previous papers have studied limiting distributions in various special cases when alpha is real, but we consider these variables for arbitrary complex alpha. Why? That's advantageous even for the study of real alpha, since it allows us to use powerful results from the theory of analytic functions in the proofs. And in doing so, we also found some interesting new mathematical phenomena for non-real alpha. I had about 10 or 15 more slides than you're actually being subjected to today in my initial attempt at this talk. And it included an outline, at least, of how things turn out for various values of alpha. Ain't nobody got time even for that, right? But I will put up one intimidating slide, intimidating for the non-probabilists in the audience, okay? So here it is. This is the case real part of alpha less than 0. So I'm making the usual assumptions, and then it turns out that if you center by the expected value of the additive functional and scale by square root of n, then you get a limiting distribution, okay? But you get a limiting distribution not only for each fixed alpha with real part of alpha less than 0, but as a stochastic process. That is, as a process in alpha, you get process convergence to a random analytic function of alpha. And you can say lots of things about the mean and covariance, but I put the things I really want you to notice in blue. It's a central limit theorem. You get, in the case of small additive functionals, case real part of alpha less than 0, you get normal distribution for the limit. You don't get that for real part of alpha bigger than a half, but I ain't got time to tell you that story, right? So, okay, so in the recent 3-author paper, we further complete the picture in the case I was just mentioning, the real part of alpha less than 0, by proving convergence of moments. Here's a story I would love to be able to tell you about the use of Hadamard products of power series that was joint work with Philippe Flageolet and Navin Kapoor. I don't have time for that. We establish asymptotic normality also for the shape functional, and we establish asymptotic normality for imaginary values of alpha. That's matching what was true for real part of alpha less than 0, but with asymptotic variance that depends only on the variance of the Galton-Watson offspring distribution, and that was true for real part of alpha positive. The asymptotic variance in those last 2 cases is maybe not too surprising, not of order n, but of order n log n. Oops, I went the wrong direction. You don't want to see that again. Okay, now due to lack of time, I'm going to be even briefer in this last technical section. So recall that for real part of alpha less than 0, to get a limiting Gaussian process, we need to center the additive functional by its mean and then divide by square root of n, okay? If you define mu of alpha to be the expected alphath power of the size unconditioned of the Galton-Watson tree, you can show that the mean of the additive functional capital F alpha has linear lead order asymptotics, and the slope in those asymptotics is this mu of alpha. So in the central limit theorem I showed, instead of centering by the exact expected value, you can center instead by mu of alpha times n. So that leads us naturally to a study of this functional mu of alpha, which for general alpha with real part of alpha less than 0 can be computed only numerically. However, when alpha is a negative integer, Svante and I found in a paper last year that mu of alpha can be computed explicitly for certain examples of critical Galton-Watson trees. And when we did that, we noticed that if we did 4 examples of critical Galton-Watson trees, you've seen the 4 examples already, okay? When you compare any 2 of them, we found that you always have mu of alpha for one case less than mu of alpha for the other case, simultaneously for all the values of alpha. And we wondered, why is that? Why do you have that ordering? So I've talked a lot about probability in this talk. I've talked a little bit about complex variables, and now finally I'm going to talk a little bit about real analysis to explain the phenomenon. By the way, in case you wonder, I got like something like 3 more slides, okay? So comparing means across Galton-Watson models, I'll give you just a whiff of the theory that we built. All right, so we built a real analytic theory to explain the phenomenon. I don't have time to tell you the full story. The essence is this theorem. Given 2 critical Galton-Watson offspring distributions, let's call them Xi1 and Xi2, with respective probability generating functions, let's call them capital Phi1 and capital Phi2. If you have one probability generating function strictly less than the other probability generating function for all real t, this is what makes it a real analytic treatment, then you have mu1 of alpha less than mu2 of alpha for all real alpha negative. The full story involves something called complete monotonicity. I don't have time to tell you about that. If you have the kind of ordering I've just talked about, then it turns out that the means for the shape functional are ordered in the reverse way. That's easy to check. And although this is only a provably only a partial order on critical Galton-Watson tree probability generating functions, surprisingly many important probability generating functions are ordered. And remember these examples from before: M-ary trees, LERTs, full binary trees, ORTs, full M-ary trees. You might wonder, why did I separate full binary trees from full M-ary trees with M greater than or equal to 3? The answer is because of the next theorem that says these, remarkably, all these examples are ordered, right? So phi1m, what were they? I don't even remember. Let me go back. The M-ary trees, not necessarily full, those increase in this ordering as M increases. They're all smaller than, for LERTs, those are all small, those are smaller than full binary, those are smaller than the ORTS example, and those are smaller than full ternary trees, and then from there on, it goes full, quaternary is larger, and so on, right? Okay, and it's really easy calculus to get that. Okay, so I'm on my last slide. I want to say, first of all, again, hello to Anita, hello to Grace, hello to whoever else is watching online. We miss you here today. Thanks to everybody who is here or watching online. Thanks to everyone who's helped me along the way. Thanks to my collaborators and my department colleagues. Some of those of you in the audience are both colleagues and collaborators. Thanks. I can't tell you how wonderful it's been to have excellent PhD advisees, including Vince and Navin and Bob, but certainly not, and Au, who I mentioned, but certainly not limited to them. And especially to the family, friends, faculty, colleagues, staff members. What would we do in AMS without our wonderful staff? And former and current students who've taken the time to join today's celebration in person or remotely. I really appreciate all of you. My last slide, here is a list of all of my co-authors with the number of papers that I've authored with them. So thanks to all of you, and thanks to these people as well.
Thank you very much, Jim. Thank you for giving us a taste of the work that you did in the time that you were here. That, of course, was just your research, but there was also the educational contributions, the leadership contributions, and we thank you for all of that. And we do have a small souvenir of today's event for you. Here we go. So, here. Oh, okay.
Thanks, Ed.
Congratulations. And I invite you all to join us for a reception. Thank you.
Yeah, it seemed too weird to.